Hello, I am Professor Maria Luisa Bainyo Salingay, asking you to join me in my short discussion on atoms and periodic table. Let us start our discussion on the important people on the history of the atom. John Dalton, English physicist and chemist, who developed the atomic theory that all matter are made up of small, indivisible particles known as atoms. Joseph John Thomson, British physicist, who was credited with the discovery of the first subatomic particle known as electron. Ernest Rutherford, a British scientist who developed the Rutherford's atomic theory that states the atom had a central positive nucleus with negative electrons orbiting it. Niels Bohr, a Danish physicist who modified the Rutherford's model. He proposed that electrons move around a nucleus but only in prescribed orbits. If electrons jump to a lower energy orbit, the difference is sent out as radiation. Erwin Schrödinger, an Austrian-Irish physicist who took the Bohr's atom model further and developed the quantum mechanical model of an atom. He calculated a mathematical equation to discover the probability of an electron occurring in different places or in a certain position. With the efforts of the important scientists mentioned earlier and other numerous scientists not mentioned contributed to the atomic structure. As you can see, the atomic structure has a nucleus wherein neutron and proton are located, while the electrons in the orbit are rotating around the nucleus. Comparing the particles of an atom, proton has a positive charge with a mass of 1.0073 atomic mass unit with the symbol P positive. Neutron has a neutral charge with a mass of 1.0087 AMU and a symbol N null. And electron with a negative charge with a mass of 5.486 times 10 to the power of negative 4 and a symbol of E negative. What makes an atom different from another atom? Atoms of the same element have same number of protons but may differ in the number of neutrons and mass. Atomic number is the number of protons indicated by subscript. Mass number is the sum of the numbers of protons and neutrons indicated by superscript. This is illustrated in carbon atom with a symbol capital C. The mass number in fuchsia is placed as superscript and atomic number in blue as subscript. What are isotopes? These are atoms with identical atomic numbers but different mass numbers. For example, carbon with mass number of 12 and atomic number of 6 contains 6 protons and 6 neutrons, while carbon with a mass number of 14 and atomic number of 6 contains 6 protons and 8 neutrons. To compute for the atomic mass of any element, it is equal to the summation of isotope mass times fractional isotope abundance. For carbon, for example, it is composed of 98.93% of carbon-12 and 1.07% of carbon-13. So the atomic mass of carbon is equal to 0.9893 times 12 AMU plus 0.0107 times 13.0035 AMU is equal to 12.01 AMU or 12.01 gram per mole as shown in the periodic table. In the periodic table, the atomic number is placed on top of the atomic symbol while the atomic mass is below the symbol. This is a periodic table. Periodic tables can be presented in various ways. In this table, the elements are classified according to its chemical properties. Metallic elements presented in this periodic table in light shade of pink form basic oxides. These elements are solid except mercury. Non-metallic elements are presented in light blue shades form acidic oxides. These elements are either liquid or gas in forms. Metalloids in light violet shades have both metallic and non-metallic chemical properties. This periodic table shows the elements are arranged by families or grouped in vertical columns. Elements in the same group have mostly similar properties. Group 1A is composed of alkali metal and hydrogen gas. Group 2A is composed of alkali earth metals. Group 3A is composed of post-transition metals and metalloid boron. Group 4A is composed of post-transition metals, metalloids, and non-metal carbon. Group 5A is composed of non-metals, metalloid, and post-transition metal bismuth. Group 6A is composed of non-metals, metalloid tellurium, and post-transition metal polonium. Group 7A is composed of halogen, and Group 8A is composed of inert gases, and Group B elements in yellow-green are called transition elements, and below it are the lanthanides and the actinides elements. Ionic charges can be predicted in the periodic table. Group 1A element tends to give off one electron and left with a charge of positive 1. Group 2A element tends to give off 2 electrons and left with a charge of positive 2. On the farthermost right column of the periodic table, Group 8A, these gases are inert. Group 7A elements tends to accept 1 electron and will have a charge of negative 1. Group 6A element tends to accept 2 electrons and will have a charge of negative 2. While transition elements can have more than 1 positive charges. Let us have some exercises on atoms and periodic table. Give the number of protons, electrons, and neutrons in neutral atoms of each of the following isotopes. For isotope carbon with a mass number of 13 and atomic number of 6, it has 6 proton, 6 electron, and 7 neutron. For isotope selenium with a mass number of 77 and atomic number of 34, it has 34 proton, 34 electron, and 43 neutron. Now let's go to the next exercise. This time, you still determine the number of protons, neutrons, and electrons, of the following isotopes that are used in medical diagnosis. But this time, it is no longer neutral, but it is charged. Before we do the first isotope, I would advise you to get a copy of a periodic table. The first isotope has an atomic number of 43, mass number 99, and a charge of positive 7. It has 43 proton, 36 electron, and 56 neutron. The name of the element is technetium. The second isotope has an atomic number of 9, mass number of 18, and a charge of negative 1. It has 9 proton, 10 electron, and 9 neutron, and the name of the element is fluorine. For the remaining 2 isotopes, try to do the exercise on your own. For the last exercise, let's do some problem solving. For the first problem, the abundance ratio of oxygen 18 to oxygen 16 in some meteorites is greater than that used to calculate the average atomic mass of oxygen on Earth. Is the average atomic mass of an oxygen atom in these meteorites greater than, less than, or equal to a terrestrial oxygen atom? You explain. Second problem. An element has the following natural abundances and isotopic masses. 90.92% abundance with 19.99 grams per mole, 0.26% abundance with 20.99 gram per mole, and 8.82% abundance with 21.99 gram per mole. So what is asked in this problem is to compute for average atomic mass in gram per mole. The third problem, average atomic masses listed by IUPAC are based on a study of experimental results. Bromine has 2 isotopes, bromine 79 and bromine 81, whose masses 78.9183 and 80.9163 gram per mole and abundances of 50.69% and 49.31% were determined in earlier experiments. Calculate the average atomic mass in gram per mole of bromine based on these experiments. How does this compare to the value given on the periodic table? That is all for today. If you have comments, feel free to contact me on the following medium of communications.